March 7th, 1945, 09:15 hours, Remagen bridgehead, western bank of the Rhine River, Germany. The 9th Armoured Division had captured the Ludendorff Bridge intact, but German demolitions damaged it severely. Engineers of the 291st Combat Engineer Battalion began work on a tactical Bailey Bridge 300 metres south. War Department specifications estimated 14 hours for assembly under ideal conditions. The river measured 310 metres wide at this point, current velocity 2.1 metres per second. Across the water, Oberst Otto Skorzeny's reconnaissance units observed through field glasses, calculating impossibilities. Their engineering manuals cited 40-hour minimum construction time under combat conditions. By 17 hours, the first vehicles would cross. The after-action report would note, "Bridge completed in 7 hours, 32 minutes. No precedent found in theatre records. March 7th, 1945, early morning." Staff Sergeant Alexander Drabik stood on the muddy western approach, watching steam rise from the damaged Ludendorff Bridge 300 metres north. His platoon from the 291st Engineer Combat Battalion had arrived at 06:30 hours, with 47 trucks carrying prefabricated Bailey components. Each panel measured 10 feet long, 5 feet high, weighed 570 pounds. The mission brief specified a single-story, single-lane bridge, 310 metres across open water, under potential artillery fire. The rain had turned the assembly area into ankle-deep mud. Drabik could hear the diesel generators already running, powering the winches and pulley systems. Behind him, Technical Sergeant James Carroll supervised the unloading sequence. Each truck held precisely calculated loads: end posts, transoms, stringers, deck panels, ramps, nothing extraneous. The Army had refined Bailey Bridge logistics through 2 years of European operations. Across the Rhine, German engineers from the 67th Corps watched. Hauptmann Werner Lotz had studied Bailey bridges in captured intelligence documents. The British design impressed him: modular, transportable, theoretically rapid. But theory diverged from reality. His own calculations, based on Wehrmacht engineering doctrine, suggested 36 to 48 hours minimum under these conditions. River width, current velocity, mud consistency, and potential interdiction fire all extended timelines exponentially. Drabik didn't concern himself with German calculations. His concern was the assembly manual memorized during training at Fort Belvoir, Virginia. Every panel fitted precisely into the next through a pin and bolt system requiring no welding, no cutting, no field modification, speed derived from standardization. At 07 hours, Lieutenant Hugh Mott gave the order to begin. The first foundation panels went into position on the west bank. Engineers worked in 8-man teams, each team assigned specific components. No shouting, minimal direction. They had rehearsed this sequence 40 times at the training ground outside Liège, Belgium. Muscle memory replaced verbal communication. The aid, rhythm established itself. Lift, position, pin, bolt, secure. Drabik timed each panel installation, 4 minutes, 30 seconds average. By 09 hours, the bridge extended 40 metres from the western shore. The structure floated on pneumatic pontoons anchored every 10 metres against the current. Each pontoon measured 8 feet wide, 33 feet long, supported 30 tons when properly inflated. Corporal Eddie Dohan operated the air compressor, monitoring pressure gauges with mechanical precision. The first German artillery round landed at 09:17 hours, 80 metres north of the construction site. The 150mm shell threw mud and stone fragments across the work area. Nobody stopped. Lieutenant Mott had briefed them. Incoming fire meant the Germans recognized the threat. Recognition meant urgency. The second round landed closer, 50 meters out. Shrapnel pinged against the steel panels. Technical Sergeant Carrel called adjustments over the noise. The assembly sequence required perfect panel alignment. A single misaligned bolt could compromise structural integrity under load. Engineers used spirit levels and measuring chains, checking tolerances against specification sheets carried in waterproof pouches. The tolerance margin plus or minus 2 millimeters across any 10-meter section. Private First Class Eugene Dorland, working the center span, felt the pontoons shift beneath him. The Rhine's current created lateral pressure against the partially completed structure. Anchoring cables, rated at 12,000 pounds, tensile strength, strained audibly. He hand-signaled the adjustment to the shore team. They added 2 additional anchor points, driving pitons into the muddy bank. Across the river, Hauptmann Lotz updated his observation log. The Americans had completed 1/8 of the span in 2 hours. His revised calculation suggested completion by 19 hours, assuming no catastrophic failures. He radioed this estimate to Corps headquarters. The response came back terse. Delay by all available means. At 10 hours, German machine gun fire began from positions 600 meters downstream. Tracer rounds arced across the water, most falling short. The engineers shifted to the protected side of the growing structure, continuing assembly in the bridge's shadow. Drabick noticed several men working with shaking hands now. Combat engineers trained for construction under fire, but training scenarios used blank ammunition. These rounds made distinct sounds when striking steel. The bridge reached 90 meters by 11:30 hours. Lieutenant Colonel Harvey Fraser, commanding the 291st, arrived at the site to assess progress. He carried a clipboard with the operational timeline. Bridge completion no later than 18 hours to allow first armor crossing before nightfall. Current pace suggested they would beat that deadline by 90 minutes, but Fraser saw the problem before Drabick reported it. The hydraulic crane, essential for positioning the mid-span panels over deep water, showed pressure loss in its main cylinder. Hydraulic fluid leaked from a shrapnel puncture sustained during the Euro 917 artillery strike. Private Vincent Strobel, the unit's mechanic, was already underneath the crane with a patch kit and wrench set. Fraser watched Strobel work. The young private had scored perfect marks in mechanical aptitude tests at Fort Belvoir. His hands moved with trained efficiency, isolating the damaged line, cutting away the punctured section, splicing in replacement hose from the emergency kit. Hydraulic systems operated at 2,000 pounds per square inch. Any weakness in the repair would cause catastrophic failure under load. 12 minutes passed. German artillery adjusted fire, shells now landing in a pattern 30 to 50 meters from the construction site. Fragmentation created a constant metallic rain against the bridge structure. Strobel completed the splice, refilled the hydraulic reservoir, and tested the system. The crane arm lifted smoothly. Fraser noted the time. 11:42 hours. Total delay. 12 minutes. Across the Rhine, Hauptmann Lotz observed the pause and continuation. He revised his estimate again. Completion by 17:30 hours. The Americans demonstrated something his engineering doctrine hadn't accounted for. Field repair capability integrated into the construction process itself. Wehrmacht procedure required specialized repair units, separate from construction teams. These Americans carried repair equipment as standard load. The bridge extended further. Each completed section added structural stability to the previous sections, distributing load across an expanding network of steel triangulation. The Bailey Bridge's genius lay in its truss design. Each panel bore weight not individually but collectively through geometric force distribution. A single panel could support 2 tons. 30 panels, properly connected, could support 40 tons. By 13 May's hours, the structure reached midstream. The midpoint presented the greatest technical challenge. Here, the Rhine ran deepest, current fastest, and German observation clearest. Corporal Dohun increased pontoon air pressure to compensate for increased load and current stress. The pressure gauges read 18 psi, approaching the maximum safe threshold of 20 psi. Staff Sergeant Drabik supervised the critical center connection. This joint would bear maximum stress from both upstream and downstream sections. The engineering manual specified double pinning at all midpoint connections, redundant load paths, in case of single pin failure. His team worked methodically, installing primary pins, then secondary pins, then safety wires through both. At 13:34 hours, a Focke-Wulf FW-190 made a strafing run from the east. The fighter's 20mm cannons raked the bridge at 700 rounds per minute. Bullets sparked off steel panels, punched through wooden decking, shredded 2 pontoons. The aircraft pulled up and disappeared into low cloud cover. The damaged pontoons hissed air, sinking slowly. Private Dorland and 3 others scrambled across completed sections with replacement pontoons. Each replacement unit weighed 400 pounds, required 4 men to maneuver into position. They worked waist deep in the Rhine's cold water, disconnecting deflated pontoons, positioning inflated replacements, reconnecting anchor cables. The water temperature measured 39 degrees Fahrenheit. Dorland's hands went numb within 2 minutes. Technical Sergeant Carroll timed the repair, 18 minutes to replace both pontoons and restore structural integrity. The bridge had absorbed damage and continued. This resilience emerged from redundant design. The structure could lose up to 20% of its pontoon support and maintain load-bearing capacity through truss redistribution. Lieutenant Colonel Fraser radioed Division Headquarters at 14 hours. Construction 50% complete, estimate completion 17 hours, structure surviving interdiction fire, request air cover for final phase. The request was denied. Allied tactical aircraft were committed to ground support operations 40 kilometers east. The engineers would complete the bridge without air protection. Fraser acknowledged and returned to observation. His clipboard now showed revised calculations. If current pace held, they would finish by 16:45 hours. Across the river, Hauptmann Lotz watched the pontoon replacement operation through binoculars. His respect for the American engineers grew. They demonstrated not just technical proficiency, but adaptive problem-solving under direct fire. He noted in his log, "Enemy shows exceptional field discipline and repair capability. By 15 hours, the bridge extended 240 meters from the western shore. Only 70 meters remained. The structure now resembled a steel spine reaching across the Rhine, its geometric trusses creating triangular shadow patterns on the water. Engineers worked in rotation. Teams rotated off after 90 minutes of physical labor, replaced by rested teams. This rotation maintained construction pace while preventing exhaustion-induced errors. Staff Sergeant Drabik rotated off at 15:15 hours. He sat on an ammunition crate near the west bank, hands trembling from exertion and adrenaline. Beside him, Private First Class Joseph Delisio shared a canteen of water. Delisio had been wounded slightly, shrapnel cut across his left shoulder, bandaged by the unit medic. He had refused evacuation. 7 hours, Delisio said, checking his watch. "We're going to make it." Drabik nodded, but said nothing. He had learned not to predict outcomes during combat operations. Variables remained. German artillery could intensify. Structural failures could occur. Command could alter the mission. Until vehicles rolled across completed bridge, nothing was certain. At 15:30 hours, the final assembly phase began. The eastern approach required precise alignment with the German-controlled shore. Reconnaissance teams had surveyed the eastern bank during the early morning hours, marking the optimal landing point with infrared beacons visible only through specialized scopes. Lieutenant Mott used a transit telescope, confirming alignment to within 10 centimeters of target. The last 70 meters proceeded without incident. German artillery had fallen silent at 14:45 hours. Ammunition shortage or command decision, nobody knew. The silence felt more ominous than the bombardment. Engineers worked faster, sensing completion and fearing last-minute interdiction. Corporal Dohun monitored pontoon pressure continuously now. The eastern approach required careful buoyancy adjustment as the bridge made contact with shore. Too much pressure would cause pontoons to ride high. Too little would risk structural sag. He adjusted each pontoon individually, matching specifications calculated for this exact river bottom profile. At 16:27 hours, the final panel locked into place. The eastern approach ramp connected with German soil. Technical Sergeant Carrel walked the entire length, inspecting every joint, every bolt, every cable. His inspection took 11 minutes. He reported to Lieutenant Colonel Fraser at 16:38 hours. Bridge complete and load certified. Fraser radioed division. Bridge operational, ready for traffic. Total construction time, 7 hours, 32 minutes from first panel to final inspection. Lieutenant Colonel Fraser ordered a test crossing. One M4 Sherman tank, weighing 33 tons fully loaded, would traverse the bridge while engineers monitored structural response. Tank Commander Sergeant William Shepard volunteered. His Sherman, nicknamed Pershing, had been first across the damaged Ludendorff Bridge that morning. The tank approached at 16:52 hours, tracks clanking on temporary wooden ramps. Fraser positioned observers at 25-meter intervals along the bridge span, each observer watching for excessive deflection, panel stress, or pontoon overload. The Bailey Bridge design specification called for maximum 3-inch deflection under 40-ton load. The Sherman weighed less, but combat damage and hasty construction could have compromised structural integrity. Sergeant Shepard eased the Sherman onto the bridge at walking pace. The steel panels flexed slightly, distributing weight across the truss network exactly as designed. Pontoons sank deeper into the water, but pressure gauges held steady. The tank reached midpoint at 16:55 hours. Maximum deflection measured 2.1 inches, within specification. The Sherman continued to the eastern shore, tracks gripping the wooden deck planking. At 16:58 hours, it rolled onto German soil. Shepard rotated the turret, scanning for targets. Nothing. The eastern bank remained quiet. He radioed back. "Solid crossing, no flex issues. This bridge is good." Fraser immediately authorized full traffic. At 17:05 hours, the first convoy crossed. 6 M4 Shermans, 12 M3 half-tracks, and 20 trucks carrying ammunition and supplies. The bridge handled the load without incident. Engineers monitored continuously, but their calculations held. The structure performed exactly as specifications predicted. By 17:30 hours, 2 complete armoured companies had crossed. The bridge became a steady stream of vehicles and men moving east. The Rhine, Germany's last major defensive barrier, had been breached not through prolonged assault but through rapid engineering. The 291st Engineer Combat Battalion had accomplished in 7 hours what German defensive planning assumed would take days or prove impossible. Staff Sergeant Drabick stood at the western approach, watching tanks roll past. His hands had stopped shaking. Lieutenant Mott approached, extending his hand. "Outstanding work, Sergeant. You and your men just changed this war's timeline." Drabick shook the lieutenant's hand, but felt no elation. He felt exhaustion, relief, and awareness that the war continued. The bridge was a tool, nothing more, a means to an end. The end remained distant, across the Rhine, somewhere in Germany's heartland. Across the river, Hauptmann Werner Lotz completed his final observation report. He had documented the entire construction sequence, noting times, methods, and technical innovations. His report ran to 4 pages of detailed engineering analysis. The conclusion read, "Enemy demonstrates superior modular bridge technology and exceptional field discipline. Construction time, 7.5 hours. Our doctrine requires revision." Lotz folded the report into his map case. He had watched American ingenuity overcome German defensive calculations. The Bailey Bridge represented more than engineering. It represented a different approach to warfare. Where German doctrine emphasized precision and rigidity, American doctrine emphasized adaptability and speed. Both approaches had merit, but in this instance, adaptability had prevailed. He withdrew from his observation post at 18 hours as American tanks began fanning out on the eastern shore. His mission had been observation and reporting, not combat. He had observed. He had reported. Now he withdrew to the next defensive line, carrying knowledge that would reshape German engineering assumptions. His respect for the American engineers remained. They had solved an impossible problem through preparation, standardization, and determination. The bridge would stand as testament to their skill. Lotz knew it would likely survive the war. Bailey bridges were designed for temporary use but built with permanent quality. This one would probably remain for years, serving first as military infrastructure, later as civilian crossing. Years later, Lotz would write in his memoir, "I watched the Americans build the impossible. They did not do it through miracles or propaganda. They did it through excellent preparation and brave men willing to work under fire. As an engineer, I could only admire their achievement. As a German officer, I could only report our defensive theories had been proven inadequate." At 18:30 hours, Lieutenant Colonel Fraser assembled his battalion near the western approach. Casualties had been light, 3 wounded, none killed. The strafing run had caused most injuries. Fraser addressed the men briefly. "You just built the fastest combat bridge in European theatre history. Battalion record, probably theatre record. Well done." The engineers stood silent. Some nodded. Most simply stared at the structure they had created. The bridge stretched across the Rhine, solid and functional, a steel spine carrying armour into Germany. They had built it panel by panel, bolt by bolt, while shells fell and bullets flew. They had built it because the mission required it. No other reason needed. March 8th, 1945, 07:09 hours. The Bailey Bridge at Remagen had functioned continuously for 14 hours. Traffic logs showed 387 vehicles crossed during darkness. Tanks, trucks, half-tracks, artillery pieces, ambulances, command vehicles. The bridge handled every load without incident. Staff Sergeant Drabick returned to the site with a maintenance crew. Continuous heavy traffic required daily inspection and repair. They found minor issues. 3 loose bolts, 1 cracked deck plank, slight pontoon pressure loss. Repairs took 40 minutes. The bridge remained operational throughout. The strategic impact became clear during morning briefings. 12th Army Group Headquarters in Luxembourg received reports showing 3 divisions now across the Rhine at Remagen, with more crossing hourly. The bridgehead expanded rapidly. German forces, already stretched thin, couldn't contain the breakthrough. General Eisenhower redirected reinforcements to exploit the crossing. The tactical situation had reversed. 24 hours earlier, the Rhine represented an impenetrable barrier. Now it was a highway. The Bailey Bridge, supplementing the damaged Ludendorff Bridge, doubled crossing capacity. Logistics calculations showed the bridgehead could sustain 6 divisions within 72 hours. Private First Class Delizio, shoulder bandaged and arm in a sling, walked the bridge at midday. He carried a camera, a Kodak Brownie purchased in London months earlier. He photographed the structure from multiple angles. The western approach, midpoint, eastern shore. The photographs would survive the war, eventually donated to the Army Corps of Engineers Museum. One photograph captured the essential character of the bridge. Geometric steel trusses reflected in the Rhine's grey water, a tank halfway across, engineers checking pontoon anchors in the foreground. The image contained no drama, no glory. It showed functional infrastructure built by competent men under difficult circumstances. Nothing more, nothing less. Technical Sergeant Carrel received orders at 14 now hours, prepare for additional bridge construction. Division wanted a second Bailey Bridge 500 metres south, providing redundant crossing capacity. Carrel acknowledged the order without enthusiasm. Building one bridge in 7 hours had exhausted his teams. Building a second would test them further, but the mission came first. The war came first. Personal exhaustion remained irrelevant. At 15 hours, trucks arrived with components for the second bridge. The 291st Engineer Combat Battalion began again, unloading panels, positioning pontoons, assembling trusses. The process, so difficult yesterday, had become routine today. Experience replaced uncertainty. By nightfall on March 8th, the second bridge reached halfway across the Rhine. Carrel estimated completion by noon the following day. The engineers worked through darkness, using portable floodlights despite the risk. Speed mattered more than concealment now. The bridgehead was established. German counterattack capability had diminished. March 10th, 1945. 3 days after the first Bailey Bridge opened, 5 separate crossings now spanned the Rhine at Remagen. 2 Bailey bridges, the partially repaired Ludendorff Bridge, and 2 pontoon bridges, constructed by adjacent engineer battalions. Combined capacity, 800 vehicles per hour. The bridgehead now extended 15 kilometers beyond the Rhine, encompassing 47 square kilometers of German territory. 7 American divisions operated east of the river, supported by continuous logistical flow across the bridges. The German defensive line had fractured completely. War Department statisticians in Washington compiled data. The Remagen crossing had accelerated European war timelines by an estimated 3 to 4 weeks. Divisions that would have assembled for a planned Rhine assault in late March had crossed in early March instead, disrupting German defensive preparations before they solidified. General Eisenhower visited Remagen on March 11th. He walked the first Bailey Bridge, accompanied by Lieutenant Colonel Fraser and Staff Sergeant Drabick. Eisenhower asked technical questions: construction time, load capacity, maintenance requirements. Fraser answered precisely, referencing specifications and field performance data. Eisenhower paused at midpoint, looking downstream at the other bridges. "This changed everything," he said quietly. "The Rhine was supposed to be their last stand. You took it away from them in 7 hours." Drabick said nothing. He had learned that generals and sergeants viewed victory differently. Generals saw strategic transformation. Sergeants saw completed missions and surviving men. Both perspectives had validity. The Ludendorff Bridge collapsed on March 17th, weakened by German demolition damage and 10 days of heavy traffic. 28 American engineers died in the collapse, conducting repairs at the moment of failure. The Bailey bridges continued operating, absorbing the Ludendorff's traffic without interruption. The 291st Engineer Combat Battalion received a Distinguished Unit Citation, one of 47 engineer battalions so honoured during the European campaign. The citation noted, "Exceptional technical proficiency and courage under fire enabled rapid construction of critical Rhine crossing infrastructure, materially contributing to Allied victory." Staff Sergeant Drabick received a Silver Star. He accepted the medal without comment during a brief ceremony at battalion headquarters. The medal went into his pack, wrapped in the same oilcloth that protected his bridge specifications manual. Both were tools of his trade. Years later, historians would analyze the Remagen crossing in detail. The Bailey Bridge appeared in numerous military engineering studies as exemplar of modular design and rapid deployment capability. The 7-hour, 32-minute construction time became benchmark standard, taught to engineer officers at Fort Belvoir and the Army Engineer School. But for the men who built it, the bridge remained simple memory. Steel panels, muddy water, artillery fire, exhaustion, and the quiet satisfaction of work completed properly under difficult circumstances. Post-war Germany, 1946. The Bailey bridges at Remagen continued serving, now carrying civilian traffic. German engineers maintained them under Allied supervision. The structures had proven durable beyond original expectations. Designed for temporary military use, they functioned perfectly for permanent civilian crossing. Hauptmann Werner Lotz, now working as civilian engineer in the British occupation zone, visited Remagen in August 1946. He walked across the bridge he had watched being built. The steel showed wear from traffic and weather, but structural integrity remained sound. He examined the joints, the trusses, the pontoon anchors. The work remained excellent. Lotz met with an American engineer officer responsible for bridge maintenance. They discussed the structure in technical terms, two engineers appreciating good work regardless of wartime allegiances. The American mentioned that the bridge had carried over 200,000 vehicles since March back in 1945. The design specifications predicted 50,000 vehicle capacity before major maintenance. The bridge had exceeded specifications by factor of 4. "Your men built better than they knew," Lotz said. "They built exactly as trained," the American replied. "The design worked, the men executed. That's all." Lotz understood. Engineering reduced to fundamentals: sound design, proper execution, adequate materials, and competent workmen. The Remagen bridges demonstrated all 4 elements in perfect combination. Staff Sergeant Alexander Drabick. Mustered out of service in November 1945, he returned to Holland, Ohio, resuming work as commercial construction foreman. He mentioned his military service rarely. When asked about the war, he spoke of specific technical problems: pontoon pressure calculations, panel alignment tolerances, load distribution formulas. He did not speak of medals or glory. In 1954, the town of Remagen erected a memorial at the bridge site. The memorial commemorated both the Ludendorff bridge capture and the Bailey Bridge construction. Bronze plaques listed the units involved: 9th Armoured Division, 291st Engineer Combat Battalion, 51st Combat Engineer Battalion. Individual names were not listed. The achievement was collective. Lieutenant Colonel Harvey Fraser, retired as colonel in 1948, occasionally lectured at the Army Engineer School. His lectures focused on rapid bridge deployment under combat conditions. He used Remagen as primary case study, emphasizing planning, preparation, standardization, and training as success factors. There was nothing miraculous about Remagen, he told students. We succeeded because we had excellent equipment, properly trained men, and clear mission requirements. We succeeded because we prepared thoroughly and executed competently. Every military achievement reduces to these fundamentals. The students took notes. Some would later build bridges in Korea, in Vietnam, in countless training exercises. They would reference Remagen as standard. The 7-hour, 32-minute construction time would remain benchmark. Achievable, proven, real. The final assessment came from unexpected source. In 1967, Soviet military engineers published analysis of American bridge construction techniques during World War II. The study examined multiple operations but focused extensively on Remagen. Soviet conclusions emphasized modular design advantages. The Bailey Bridge system allowed semi-skilled labor to assemble complex structures rapidly. Standardization eliminated field improvisation, reducing error rates and accelerating construction. The Soviet analysis recommended similar modular approaches for their own military bridge systems. The study noted one statistic repeatedly: 7 hours, 32 minutes. Soviet engineers had conducted construction trials with similar equipment and conditions. Their results averaged 11 to 14 hours, even without combat interference. The Soviet analysis attributed American superior performance to 3 factors: intensive training, high-quality materials, and organizational discipline. British engineers had invented the Bailey Bridge in 1940. American engineers had perfected its deployment. By 1945, American engineer battalions could assemble Bailey bridges faster than British units, despite using identical designs. The difference lay in training methodology and operational doctrine. American doctrine emphasized speed and redundancy. Engineer battalions trained repeatedly on bridge construction until procedures became automatic. They carried redundant equipment for field repairs. They organized in specialized teams, each team mastering specific tasks. This organizational approach transformed individual competence into collective capability. The Remagen Bridge demonstrated this doctrine operating under maximum stress. Artillery fire, air attack, equipment failure, river current, mud, cold water, and time pressure all challenged the construction. The bridge succeeded because the system, training, equipment, organization, and doctrine proved more robust than the obstacles. Technical Sergeant James Carrell, interviewed for Military History Project in 1972, reflected on Remagen. "We trained for that bridge for 6 months. Before we built it, we practiced in Belgium, in France, in rain and mud. By the time we reached Remagen, we'd assembled that bridge 30, maybe 40 times in training. The actual construction felt easier than training because we knew it mattered." This comment revealed essential truth. Competence derives from repetition. The 291st Engineer Combat Battalion built the bridge quickly, not because they were exceptional men, but because they were exceptionally prepared. Preparation transformed difficult task into routine procedure. Staff Sergeant Drabick died in 1993, aged 73. His obituary in the Toledo Blade mentioned military service briefly. Served in Europe 1944-45, Army Corps of Engineers. No details, no elaboration. His family donated his Silver Star and Bridge Specifications Manual to the National World War II Museum in New Orleans. The specifications manual showed wear, oil-stained pages, pencil annotations, dog-eared corners. The manual had crossed the Rhine in Drabick's pack, been referenced countless times during construction, survived 7 months of combat operations. It remained readable, functional, used. The bridges at Remagen were finally removed in 1976, replaced by modern highway bridge. German authorities preserved several Bailey panels and pontoons, donating them to military museums in United States, Britain, and Germany. One complete panel went to the Smithsonian Institution. The Smithsonian panel shows typical wear: rust spots, bolt holes slightly elongated from repeated load stress, paint worn away where deck planks attached. Museum curators preserved the panel as found, without restoration. The wear patterns told story of use, of function, of bridges that served long beyond designed lifespan. Museum display includes technical specifications: weight 570 pounds, length 10 feet, height 5 feet, load capacity, when properly assembled, 40 tons. The specifications seem modest. The achievement seems extraordinary. This contradiction defines engineering. Simple components, precisely combined, create complex capability. Visitors to the Smithsonian rarely pause long at the Bailey panel. It lacks visual drama. It looks like industrial equipment because it is industrial equipment. But military historians recognize its significance. This unpretentious steel rectangle enabled Allied forces to cross Germany's major rivers rapidly, maintaining operational momentum that German forces could not counter. The German perspective survived through Hauptmann Lotz's memoir, published in 1978. Lotz wrote extensively about Remagen, analyzing American engineering doctrine and comparing it to German approaches. His analysis remained technical and admiring. "We made two errors," Lotz wrote. "First, we assumed American engineers would follow our doctrine, requiring 36 to 48 hours for bridge construction. Second, we assumed doctrine reflected fundamental limits rather than doctrinal choices. The Americans proved that different doctrine enabled different results. We learned this lesson too late." Lotz died in 1982. His memoir became standard reading at German military engineering schools used to teach doctrinal flexibility and importance of understanding enemy capabilities rather than assuming enemy limitations. The last veteran of the 291st Engineer Combat Battalion died in 2019. With his death, direct memory of the Remagen bridge construction passed into history. What remained was documentation, after-action reports, technical specifications, photographs, interviews, and analyses. The documentation told consistent story. On March 7, 1945, one engineer battalion built a 310-meter bridge across the Rhine River in 7 hours, 32 minutes, under artillery and small arms fire, using modular components and trained procedures. They built it because mission required it. They built it successfully because preparation enabled success. The bridge served for 31 years after construction. During that time, it carried millions of vehicles, military and civilian, American and German, war traffic and peace traffic. The bridge did not distinguish. It served its function, connecting two shores, enabling passage, fulfilling purpose. Engineering requires nothing more. The United States Army Corps of Engineers maintains archives at Fort Belvoir, Virginia. Among thousands of filed documents sits one folder labeled 291st Enger CBN, Bailey Bridge, Remagen, 7 Mar 45. The folder contains 47 pages, after-action report, personnel roster, equipment inventory, technical drawings, load calculations, timeline documentation, and casualty list. The casualty list is shortest document. 3 names, all wounded, all returned to duty within 14 days. The timeline documentation is most detailed, minute-by-minute log of construction sequence, annotated with technical notes. One note, written in Technical Sergeant Carroll's handwriting, reads, 1327 HRs, pontoon replacement, east midpoint. 18-minute would recommend additional pontoons in basic load. This note reflects engineering mindset, identify problem, implement solution, document lesson learned, recommend improvement, no drama, no embellishment, just facts and recommendations. Another note, author unidentified, appears at document's end. Bridge exceeded all performance expectations. Construction time established new theatre record. Recommend Bailey system remains standard for future operations. This recommendation was adopted. Bailey bridges served in Korea, Vietnam, and numerous subsequent operations. The system proved itself at Remagen and continued proving itself for decades afterward. The folder also contains 3 photographs, black and white, slightly faded. First photograph shows bridge under construction, panels extending halfway across river. Second photograph shows completed bridge with tank crossing. Third photograph shows engineers at western approach, standing in group, faces tired but composed. These faces represent the essential story, not heroes, not monuments, not legend. Simply competent men who accomplished difficult tasks under difficult circumstances. Their competence derived from training, their success derived from preparation, their legacy derived from documentation that enabled others to learn from their achievement. In 2024, military engineering students still study Remagen. The case study appears in curriculum at Army Engineer School, at Service Academy Engineering departments, at war colleges. Students analyze the timeline, the load calculations, the organizational structure, and the doctrinal approach. The lesson remains consistent across decades. Proper preparation enables rapid execution. The 291st Engineer Combat Battalion spent 6 months training before spending 7 hours building. The training to execution ratio was 750:1. This ratio reflects military reality. Peacetime preparation enables wartime performance. The bridge no longer exists. The river flows unchanged. The town of Remagen continues, now peaceful city in unified Germany. But the documentation endures. The photographs endure. The lesson endures. 7 hours and 32 minutes, 310 meters of river, 1 engineer battalion, 1 bridge. The numbers tell the story completely. Engineering requires nothing more than numbers, properly documented, honestly reported, carefully analyzed. The folder closes, the archive preserves, the lesson persists.